All right, so let's get going. We have quite the lineup for the lightning talks. We have no less than 14, so I hope you guys are ready. So for everyone who's speaking in the lightning talks, add your slides directly on Indico on the website, and we'll just try to stick to one laptop. I know some of you have demos to show, so we can plug for those. But for the slides, we'll just try to use the same laptop, so that way we can actually go through 14. So yeah, the first 4 or 5 are already in here, so we're good to go. So Simon, you can kick it off.
Yeah. Hi again. I'm still named Simon Sir, and I'll talk about Wayland. No. We organized a little workshop to make KMS planes useful for users, for compositors. So the basic idea is that hardware has some hardware planes, and to save battery and improve latency, we really like to skip composition and directly scan out client buffers and some hardware planes. The issue is that compositors right now, they don't use KMS planes at all, at least overlay planes, except Western, but it's still not complete, and yeah, it's complicated. So to fix this situation, I've begun to work on a little experiment, libliftoff. It basically does, you give it a sine graph, and it maps the sine graph to hardware planes when possible, and it uses as many planes as possible. So generally, people seemed like quite interested in it. So there are two types of people in the room. There are some compositor writers. So KDE people seems pretty interested. So I'm a WL Roots people, so of course I'm also interested. Western people have their own implementation, but apparently they would like to they don't want to maintain this code, so they're interested too. I still need to talk to GNOME people. And the other type of people in the room were so KMS developers, let's say. And yeah, it seems like we're pretty interested in doing this. It's a good idea. There are a couple of issues. So right now it's just a prototype. It works, kind of. So we just need to turn it into a real thing. There are still some issues with multiple outputs, because when you have only one output enabled, then it starts using all the planes. If you plug in some other outputs, maybe you won't be able to use planes and this output. And since both output timings are not aligned necessarily, you cannot really balance planes very easily between the two. So that's something we need to figure out. And maybe it's a good idea to allow compositors to provide priorities on some layer, to say this layer is very is focused, is the focused window, so I'd like to put it on a plane. It's more important because it's what the user interacts with. And there are also a couple of longer-term plans. So basically the problem is that libliftoff only uses current KMS API with atomic checks. So that's cool because it works on all drivers, but to be able to better manage plans and see more optimization opportunities, maybe we'll need to have some vendor plugins. So basically one library per driver. And so it's kind of so related to the second point, which is the compositor should say to clients, hey, you're using this format, but if you were using this other format, I could put you on a plane, and that'd be really cool. So I have a patch to change the Wayland protocol to be able to do this. So yeah, to provide these hints, it will be easier if we had better knowledge on the driver. So having vendor plugins would help having better hints too. And we were discussing in the Allocator discussion also about liblib stuff. Maybe that could help too, but yeah, it's not clear yet. Maybe it's better to do the transition, the clients. Yeah, thanks.
Hello, Neil Roberts again. So I'm just going to do a summary of the breakout session we had after the Mediump talk. So yeah, from the talk and the questions, there were quite a few issues raised. So we had a 2-hour breakout session to try and discuss the issues and make a plan for how to move forward with that. So I'll list some of the problems and some of the solutions that we came up with. So one of the things is that we can't merge the piglet tests that I made for the branch because, yeah, they check that the lowering took place, but not doing any lowering is valid spec behavior, so it can't work as a general test. So the idea is that we're going to write unit tests directly in the Mesa tree. So in that, because it's in the Mesa tree, it can just directly invoke the lowering pass and check in the IR tree that it did actually do some lowering. So I actually just made a start on this as well already. I just added a lower precision option to the standalone compiler that's built into Mesa. And then there's like a little Python unit test that just greps the output of that to check that it did some lowering. Okay, so the other thing, there was some concerns about the lowering pass relies on a later NER pass, which removes redundant conversions. So one of the conversions that we want to remove is going from float 32 to float 16 to float 32. So in the case of the lowering pass, that's okay because yeah, the conversions generated by the lowering pass and they're not visible to the application. But if the driver was ever used in a case where float 16 types were added to DSL-ES, that would become a problem because obviously this conversion is not lossless, so it's not safe to get rid of it. So to be future-proof, we want to not do that. So the idea is that instead of lowering to a float 32 to float 16 conversion, we add a magic new opcode to both the DLSL IR and to NER to lower to a magic Mediump type, which does exactly the same thing as lowering to float 16, but it tells the lower layers that it's okay to remove this this conversion because it was generated specifically for the precision. And then the idea is that we would have a later pass after that that could just lower that back again to the hard conversions to float 16, so that the driver layers don't need to know about this opcode. So there was quite a lot of controversy when we said that we wanted to change NER so that it could have a different dest size from the source size in an instruction, because we want to fold the conversion operations into the ALU instructions. So yeah, this is not a nice thing to do because lots of drivers might be making assumptions that that this isn't the case. So just changing it at this late stage is not very nice. So yeah, just simple solution is just to make the folding IR3 specific and just do it as part of the code generation. So the piece that generates the IR3 opcodes can just peek through the NER and see if it encounters a conversion. If that came from an ALU operation, just generate the ALU operation with the conversion directly instead of outputting the conversion. So Connor suggested that we might be handling the built-ins a bit too late, a bit wrong, because the way that the pass is seeing them, it sees them as actual opcodes, and apparently early on in the GLSL IR, they just appear as normal function codes, function calls. So if I'm seeing them as built-ins, that means we're doing the lowering pass too late. So we're just going to look at that and try and make sure that the lowering pass is really the earliest point possible, and then check that it still handles the built-ins even if they appear as function calls instead of as built-in opcodes. So those are the short-term issues, so that we should hopefully be able to get those fixed quite quickly. And then the idea is once we get those simpler issues fixed, we can land the merge request. And yeah, so this lowering pass will end up just, to begin with, will just be a Freedreno-specific lowering pass, and it will be opt-in with a debug option. So it will just be start with just for testing. And yeah, and if we can get it into the upstream, obviously that would be great to keep it, to avoid having to rebase all the time. So in the long term, we want to do a more complete solution so that instead of the lowering branch adding conversion operations all over the place, it would have a marker on all of the operations to say that this operation can be done in Mediump. So the lowering pass becomes an analysis pass that marks any possible opcodes as being able to be done in a lower precision. And then we have to transmit this metadata all the way down through NER and check that it survives all of the NER optimizations. And then at the latest stage possible, you can use that information to generate float 16 instructions. So that should be able to generate much better code. And that will be future-proof as well for when we want to do something similar in Vulkan to handle the SPIR-V precision markers in Vulkan. So that's going to be probably a lot more work because, yeah, well, we might need to audit all the optimizations to make sure that they correctly handle the precision metadata. But yeah, ideally that would be the ideal solution. So okay, that's everything. Thank you.
Okay, so I'm gonna present the minutes from the Mesa CI workshop. So we talked about quite a few things. I tried to group them into topics. So we spoke about the infrastructure first, and so currently in Mesa Master, there is a GitLab orchestrated testing. So it's not just GitLab, but there's also Lava, but Lava is hidden. So GitLab is the orchestrator, so that's the most important part. And everyone agreed that we should continue working on this. So that means that we would have more hardware farms and everything. Then to make reading the results more accessible, it should be augmented by an external website, like so it could be Intel Mesa CI that would be used, or we could have something that is based on Grafana and Prometheus, and that would allow to see trends and to also set up alerts like, oh, there's a regression here, and actually sending an information to whoever is interested. So that would bring a bit more than just this pass-fail on every single run. Then on the test suite side, so currently we use the QP 2 and 3 for testing GLES 2 and GLES 3. And we want to grow towards trace-based testing that would bring rendering correctness of multiple games, but also some performance testing. So on the hardware side, so what is Mesa tested on? So right now, at first there was LLVM pipe and soft pipe that landed, and quickly after Freedreno came on a couple of boards. And now we're planning on adding more hardware farms. That would be Panfrost or Radvi or Lima. And now for the traces, so the way we would do this is, so VK trace has been a little problematic and inconsistent in its behavior. So LunarG has been working on a new tool that is called Graphics Reconstruct, which is much better at trace trimming, which means that it could cut the execution time by multiple orders of magnitude, depending on how many scenes you want to have. And that may make the traces suitable for pre-merge testing. So that would be quite beneficial and would add more testing than just unit testing. And for performance and correctness testing, the problem is that all these traces, when we run them, it takes over, basically it's like a day, in the order of magnitude of a day. And so we cannot use it for testing every commit, but then we need to run it periodically. And if we have regressions, they could be auto-bisected to find the cause, and that would help filing bugs and putting blame on people. On the person introducing the regression, so speeding up the fixing. And yeah, for the last part, this is something that is possible. EasyBench has been doing this for a while. That's it. Thanks.
So we had a workshop about cameras, and especially interoperability between cameras and graphics and display, but also focusing on just the camera side to see whether more collaboration could be possible and what we could do better. We have identified and talked about a few of the interoperability problems that we have today. We have the MA support on both sides that on paper works really great to share buffers. In practice, cache management is broken, at least on the V-File2 side, or at least the contract between the two is not respected, so cache doesn't work. We also have a problem with missing support for fences in V-File2, so that's going really great. It's a problem that's been there for quite some time, especially for cache handling. There's a fix that has been developed and is available. It's been available for a couple of years, I think. But due to the frameworks that use inside the kernel, the complexity on the V-File2 side, that fix also breaks a couple of other use cases. So it's one fix and a few regressions, and nobody knows how to really fix that. So not great. We talked about the documentation as well. We have extensive documentation on both sides. DRM KMS is doing really great when it comes to documented the in-kernel API, and V-File2 has historically focused on the other side for use space API. And in both cases, we miss a bit of a really high-level view of how the pieces fit together. So I think there are lots of opportunities for cross improvements and possibly cooperations. We do document, for instance, for CCs on both sides, and it doesn't make sense. Even if we don't have right now a common definition, it doesn't make sense to duplicate documentation for formats that are the same. We talked a lot about camera and display and pipeline configuration. There are lots of different formats and constraints that you can have depending on your devices, and the reconciliation is definitely a hard problem. DRM KMS reports some information, not everything. We don't really have information that we can query regarding what kind of alignment is required. So it's kind of limited. It's something that we need to solve in user space. Has been solved in GStreamer, for instance, for quite some time, but that has taken a lot of time to develop proper solutions for. So for other user space frameworks, it's still painful. That will require a bit of extension on the DRM and KMS side in order to report more information, but eventually the arbitration will need to live in user space anyway, and that's something that has been discussed for at least a couple of years now. When it comes to enumeration and configuration, we have two very different models. On the DRM and KMS side, we are very static. You can enumerate the formats that you plan support, how many planes you have, and a bunch of static information at init time, and that's it. And when it comes to configuration, you queue an atomic commit, it's rejected or accepted, and if it's rejected, you have absolutely no idea why. So as long as the configuration is fairly simple, you can have heuristics in user space, where you can say, okay, I'm going to retry with one less plane, and hopefully that's going to work. In V-File2 for cameras, on the other hand, we have much more dynamic configuration and much more dynamic enumeration as well. Mostly due to the nature of cameras that require way more configuration parameters and more fine-grained configuration. But that's very powerful, but very complex and hard to implement and use, and leads to different behaviors between different drivers, which is definitely not ideal. So DRM KMS could benefit from more dynamic and a negotiated approach, but Daniel Vedder mentioned that he's a bit worried that it would open the door to doing lots of dirty stuff in the drivers, and that we need to make sure that they won't get it wrong. So one possible solution would be to report some kind of failure hints when you do an atomic test, to at least to flag the parameters that were wrong on and not possible to support with the others. That will need to be very carefully considered and solved for cameras in general. And even if the implementations are separate for cameras and graphics, having a common mechanism with a similar way for user space to do the configuration and the discovery would be useful, because when user space has to deal with both cameras and displays, they have to learn two completely different methods of doing that and use two different mindsets. That gets quite difficult. Last slide. New camera API. So this is not specific to display as such, but we know that a camera atomic API is needed. We also know that it took 5 years roughly between the time it was initially discussed in KMS and the time when the KMS atomic API was there. We needed 2 more for cameras, so a few shortcuts would probably be needed. Very fortunately, we'll be able to benefit from all the lessons learned on the graphics side, hopefully. It has also been mentioned that VFL2 has a tendency to be developed in bursts, so when someone really has a pressing need and has money to put behind that, development happens and then it goes silent for a long time, which is not ideal to develop such a new feature. So how could we do that? It's hard to do on top of VFL2 as it exists today. We have way too many syscalls that we need to call. We have lots of legacy code, especially inside the kernel, that makes it very difficult to refactor things. So it would be really cumbersome and not nice to use, neither for user space nor for the kernel. Could DRM KMS come to the rescue? Some people have mentioned that we could have a camera API inside DRM and KMS. That would be nice to share code for write-back bridges and other components. There are drawbacks too. Do we need something new? Are we suffering from the not invented here syndrome? It's a bit too early to tell what we need to do, but at least there was a clear interest on, well, moving forward suddenly, of having a solution, and no rejection of going something that would go against the usual path that we take, and something else that just extending VFL2 could be accepted, at least by the people in the room. Thank you.
Hi, I'm Andy Ritger. James had to run and catch a plane, so I'll try to represent what we talked about in the Allocator workshop earlier today. So just kind of a restatement of the problem that James has been wrestling with. So you know, when we're allocating buffers and using them for different things, you know, the challenge is how to select a format that's possible at all for all the uses that we want to use it for, and then ideally pick a format that's optimal for each of the uses. That's part of the problem, and then the other part is transitioning the format of the buffer when we're using it for different things. And the example that James gave in his talk that I find it's probably the easiest one to think about is, you know, rendering, and you know, James had some compelling numbers for, you know, wanting to render compressed, and then if you're going to use that for texturing, you know, leave it compressed, but if you want to use it for scan out, then needing to decompress in place. And so finding the right place to do that decompression is really the crux of this. So in the workshop, I think we all agreed that, you know, we should not try to strive for, you know, any sort of all-encompassing solution. You know, this is dragged down a long time, partly because we're trying to solve too much. So focusing on trying to do things incrementally where we can. It's sort of a balancing act, because, you know, we are trying to change. You know, there's potentially changes in lots of different APIs, Vulkan and OpenGL, EGL, and so on, and we don't want to have to make changes in each of those things more times than necessary. So on the one hand, we'd like to figure out what we want, what the right thing should be, so that we only need to change each of those once. But, you know, on the other hand, we also want to make forward progress. But I think overall, the design principle of change things incrementally. And specifically for the workshop today, we tried to focus on the issue of defining those transition cases, and you know, how to address that. And you know, again, the case of rendering to a buffer and then you know, either texturing from it or displaying from it. So this ties in nicely with the discussion for lib liftoff and the idea of the compositor when it's going to take some series of buffers and present them, it's really at that point in time that it needs to decide, trying to use the DRM KMS atomic APIs, can I use the display hardware to display all of this, or do I need to do some amount of compositing and figuring out how to make most optimal use of the display hardware. And that decision then impacts this transition. If you're going to fall back to compositing your thing together, then you want to keep the surface, keep the buffer compressed. But if you decide that, I can use this for, if I can use the display engine to display all these buffers separately, then you need to decompress in place. And so we really can't do that transition any earlier than when we make that decision about how to use the buffer. So we discussed the idea of lib, trying to centralize more of this logic in lib liftoff and have lib liftoff be the thing that reports back to the compositor whether or not that sort of transition is required. And then the compositor itself would be responsible for using whatever rendering API it's using, OpenGL, Vulkan, or whatever, and then new extensions that we would need in those to perform that transition. And possibly also, and I think it's already been mentioned, the idea of providing feedback back to the client. Is there a more optimal buffer format that it could be using? So some next steps from here. I think James didn't mention it during his talk, but one of his slides has links to all of his prototype patches. He'll push those as merge requests so that we can start looking at that and thinking about what makes sense there. And focusing and cleaning up some of those. I think some of the format modifier stuff in Nouveau probably makes sense on its own. So let's work through the review on that. And I think, at least from NVIDIA's perspective, we're pretty eager about lib liftoff. So we want to work more, keep driving that project forward. I think longer term, James is pretty interested in also solving the constraint definition problem. The example that he gave during the talk of I think it was AMD and Intel and allocating a buffer but not getting the pitch right such that that buffer could be shared. It would be nice to solve that problem, but I think we can solve a lot of these other pieces independent of that. So in the spirit of doing things incrementally, I think that'll be follow-on work. So that's what I have. Thank you.
So hello, I'm Arek, and I'm one of the maintainers of IGT GPU Tools. So quick explanation what it is. It's a collection of test tools for developing the DRM drivers. So it's like a low-level test that poke a couple of IOCTLs and expect something sensible to come out of it. So one of the biggest issues we had was lack of documentation of the tests. So we had the core APIs and everything else documented, but like the tests were hard to understand because we had just the name, which was usually quite short and that didn't explain things well, and the code itself. So now we are mandating to each subtest to have IGT describe, or a block of tests to have IGT describe that describes it in a human readable manner. And it's not supposed to be like a English, C2 English translation. It's supposed to be like a grander idea behind the test, what kind of things you want to test or like express through that test. So it's required for all new tests that are coming into Trio as of now. If you forget to include that, you will get nice email pointing you to the documentation with the examples, do's, don'ts, and a couple of example patches that already introduced those descriptions for existing tests. You can access those either as a generated HTML documentation or just on a like binary level using -- describe. So another thing that has changed since last year is GitLab CI. So we started using that. We're still using mailing lists, and yet we are using GitLab CI for everything pre-merged. So we have a thing that downloads patches from the mailing list, applies it to a tree, pushes it to a separate Git repository, triggers all the pipelines, checks for the status, and then sends an email to patchwork. So it's kind of complicated, but at least people find it helpful. So what it does, it cross-compiles IGT to a couple of platforms. So it's x86, ARM64, ARM hardfloat, and MIPS, and runs at least the internal framework consistency checks. It also compiles using Clang, so to make sure that we don't break stuff for Android people or Chrome OS people. it also, this is the bit that does the docs enforcement. So this is the thing that finds all the new tests introduced by the commits that are not documented, and also generates runnable containers. So this is something that helps when you run CI farm or when you want just run a couple of IGT tests on your machine. Traditionally, you had to install the dependencies, compile it yourself, or like download binaries from random stuff, whereas this is like 100-ish megs base layer plus 8 megs of IGT on top. You just download Podman or whatever, run it in privileged mode, and here you have IGT output. So this is really helpful. This will be documented in README. The patch, including that, is on the mailing list right now. I just sent it yesterday. And we are planning to use that in our infrastructure for running IGT in an automated way. So other notable things is that we had a couple of Panfrost tests added, so welcome to the family. I'm really happy to see them. We had great work done by Simon Sir on Chameleon. So it was reworked. It was like the core of IGT, the core for supporting Chameleon was much improved by him. He added tests for audio. He added some link failure training, much more EDID tests. So this is really, really cool work. Also, discovery. So with Chameleon, the issue previously was that you had to do the port mapping by yourself. That means that like what kind of connector on the machine side corresponds to which Chameleon port. Now this is being auto-discovered through EDID. So basically each one gets a unique EDID and we auto-discover that way. You can still provide like a fixed configuration if you want to have consistency checks. So because sometimes something might be very broken. So other things, IGT Runner was maturing. So we replaced Piglet with IGT Runner that is slightly more targeted towards running IGT, and there was multiple improvements in how we handle watchdogs, how we parse the results. So it got much better, and we run it like we use it to run 6 million tests a week on our farm. So this was a lot of issues and a lot of like sporadic race conditions, and most of that stuff was ironed out. What is grayed out here is LS GPU and multi-GPU, because this is currently in flight. So IGT is going to get a new tool called LS GPU, which shows you the topology of DRM render, like DRM nodes in dev, and also all the information that we get about the devices providing those from UDEV. As well as like sys paths and dev paths. So this allows you to just explore and see what's going on, what you have in the system. And the multi-GPU support means that you can use that information to run IGT on dedicated GPUs. So in case you have machine with multi-GPUs, and currently IGT was defaulting to Intel, then like I think next line was AMD and things like that. So with multiple GPUs, you are able to specify exactly what you want to run. You can use sysfs path, you can use UDEV properties, and then this is going to be extended for tests that run between multiple GPUs. So for example, prime tests. So if you have a prime test and you want to share buffers from one GPU to another, you would be able to specify which one you want to share from which. And I guess that's it. Thanks for contributing.
Okay, so this presentation is about kind of like a throwback to the old days, reviving vintage underserved graphics hardware on the xserver. So when I use the word like vintage or underserved, what does it mean? So the first time I heard the word underserved was like when it was about something about some neighborhood where the taxi service is kind of basically underserved in terms of they don't get enough of it. And that was many years ago, before like smartphone and rideshare services existed. So it's definitely more than 10 years ago. This word underserved is not really, a recognized dictionary term. So it give you that, that thing that you misspelled something. However, recently I read an article that there's one state in our country, United States of America, that they only have like one medical doctor for like really large amounts of land, and basically nobody wants to be a doctor there. And they use the word underserved multiple times in that article. And, that kind of reminded me that, there's a lot of graphics hardware out there that people used to use about maybe 15, 20 years ago that, never really got much attention, especially in the last, let's say, 10 years or so. And these are the kind of challenges of dealing with like old hardware. And one of it is that when they got rid of XAA, some of the developers kind of broke the code. I saw a couple devices that were like that. And another problem is like the code quality was like really, really poor. It's the x386 era, and you know, it's kind of pretty bad. And then the hardware, of course, itself is pretty underpowered, and you know, some of them have like only 1 megabyte of frame buffer, and some of them don't even have automatic detection of the monitor, VGA, of course, and some of them don't have 32-bit BPP, which means you use 4 bytes for the pixel. Some of them are actually 3 bytes, 24-bit BPP, and that causes a lot of issue. xserver 1.20 got rid of support for the 24 BPP. And then some of it is like, you know, it's hard to obtain some of these kind of little minor cards if some people recognize them. So these are the kind of the approach I will take for how I will maintain the code. First, like try to fix things. If it used to kind of nominally work before when XAA existed and it doesn't work now, that means that somebody broke the code. So try to fix that, and get rid of also compilation warnings, which is very annoying when you compile code. And then also like get rid of like these tab white space issues and indentation. White space could be done automatically from using tools, but the indentation is a little trickier. It takes a lot of time, and it's kind of pretty boring. And then after you do all that, do an archive and release it so that, you know, if somebody doesn't like my work, they could just use the old one. And this is the approach of what I will do beyond just maintenance is, you know, I will try to like do, since I've been working on Open Chrome DRM for like a couple years already, I have some experience with that, and it allows me to like basically be able to put some newly written code into Open Chrome DRM and make sure it works, and then I could then feed it back into like a new DRM to serve these devices, and then also try to change that DDX and do dual mode UMS, KMS, dual support. So doing that, I will be I'm currently working on another DRM other than Open Chrome DRM. And it will be Trident Microsystems, and then, you know, Trident is probably, some of you don't even know, is like those $30 graphics cards at a computer dealer that nobody really wants. They often went into those graphics cards. And I don't have a public repository yet. Eventually, I have to figure out how to do that and all that. In terms of the actual, you know, maintenance work, I did actually ship xserver 1.19.7. I think only Open Indiana and one of the BSD distributions took it. I don't think any of the Linux people took it. This is really a kind of fix for my this sys6226 chip. And these are the other maintenance work I did. I got rid of like a lot of compilation warnings so far. These are like really old devices, I understand. And this is the conclusion. Basically, you know, vintage is really kind of nice way to call it, but it really is underserved. Maybe xserver itself is becoming like that gradually. Maybe somebody have to do something about that. And then I've been doing, you know, the breakage fix, and then leveraging the Open Chrome experience, and also doing DRM is really, really like painful. So it's not for like a new person. You have to get a mentor. That's all. Thank you.
We started writing a new kernel driver that can be mainlined in January, and it was merged in 5.2. It's quite small. It uses a lot of the helpers in the kernel. It's only 4,500 lines of code. Keybase, for comparison, is 7,000 lines of code, but it also does a lot of other stuff. It's interesting that we already support separate address spaces, so that one process cannot mess with the memory, with the buffers from another process. We support dynamic frequency scaling, GPU reset that really works. We have a memory shrinker that when there's memory pressure, we can release buffers that are in the cache that user space manages, but tells us with madvice that it's not really needed at that moment. We can release that. It's a lot of memory. We have some performance counters that we can provide to user space, and we have tests for the kernel, IGT tests, as was mentioned before. But probably the single most important thing is that ARM is contributing to it. So we wrote it, sending it there, and then ARM2Kit, and then running with that. And that's from the kernel. We can move to user space.
On user space, we've been productive. I know none of you are going to listen to anything I say in user space, we've been productive. I know none of you are going to listen to anything I say whatsoever because you're all watching Super Tux Carve in demo mode. This is running with the Panfrost driver on my Chromebook. What? This is mainline kernel, master Mesa as of this morning, all 100% free software. So since last year XDC, we had Leod and I did our talk, and we had our GL Mark spinning cube. So we've got a little bit done since then. Just a little bit, you know, have a out of order scheduler, pipeline jobs, fun stuff. So it's been pretty cool, and we're upstream and we're real, and we are in the major distributions now. I know Fedora has been experimenting with us. We're in Debian unstable and should be getting into testing shortly. We exist. Ta-da.
So what's next?
What's next? Hopefully Bifrost. GLES 3 support as well. This is desktop GL2 running here, but everybody loves fancier graphics because this isn't fancy enough, so GL3. And also we are looking into getting ARM frame buffer compression working across the stack, so you can have content compressed and all the way from the app down to the display. So
on the kernel side, we don't have as much work to do. We want to add thermal support, so we have a cooling device which will clock down the GPU when there's thermal issues. And we need some bits changed for Bifrost, mostly in the device tree and the MMU. And we'll need for Vulkan user space control GPU virtual addresses. So user space will be in control on allocating addresses for the BOs. And we also need to get those IGT tests in kernel CI and keeping an eye so things don't break and extend those as well. And that's all, I think.
thank you.
Hi, I'm Eric Anholt. I work at Google in the Chrome OS group. I've been working on the Freedreno driver, but I took a detour to work on improving the Mesa CI system based around GitLab. I am really inspired by the creator of Rust's not rocket science rule of software engineering, which is automatically maintain a repository of code that passes all the tests. What this means is if you care about this test, you should be running it before you merge code every time. Make sure the tests stay green. So what do we have available to help us with this? GitLab, our Git hosting service that we use for freedesktop.org, has integrated CI with it. You specify in your repository a little YAML file. I'm not a fan of YAML, but yeah, I've learned to work with it. Specify a bunch of jobs to run. Jobs are basically just shell scripts or a small set of commands. You get to specify dependencies between your jobs, so you can have a build job and then multiple test jobs that consume that. The jobs communicate to each other using artifacts. So artifacts actually get uploaded from the job run on one runner to freedesktop.org, stored there for 4 weeks by default. And that way, other jobs can pull them down, or if something goes wrong, a developer can go pull down those artifacts and take a look at that driver that got built. Jobs can be tagged to require a specific set of runners. So we do this on freedesktop.org. We have an ARM runner that's tagged ARM64. And that way you can segregate jobs. You know, I only really want to be building normally on x86, but sometimes I really want to build something on ARM, and we can tag a job to that specific runner. I also use this for my hardware testing. So I have a set of hardware tagged DB410C for the DB410C boards. I've got a bunch of Chesa boards. And finally, jobs can use Docker images and spawn their scripts inside of there. So the GitLab runner takes care of pulling down your Docker image and setting up Docker and spawning it and getting the shell script that from our GitLab CI stuff into that image. What do we have for runners? Mesa mostly uses freedesktop.org's shared pool of x86 64 runners. These are a set of runners donated by Packet.net and the GStreamer project. They're big, beefy Intel systems. So these do things for us like the Docker container builds that we use to build Mesa so that we have a nice stable system image that builds Mesa. Our compiler doesn't change from underneath us until we decide to make it change. Also, our DEQP test. DEQP takes forever to build. So do it once, cache that container forever. So the x86 64s do Mesa builds. They do the unit tests. They also do our cross builds to ARM and actually run the ARM unit tests on x86 using QEMU. We also use these to do DEQP runs for GLES2 and GLES3 with the software rasterizers. So we actually can make sure that when we make changes to Mesa, at least some renderers still work. As I mentioned, freedesktop.org has one large shared ARM runner that we can use for big builds if you need to do a big build on ARM that's not suitable for cross-building. Yeah, trying to do Docker image builds under QEMU was awful. Don't recommend. Finally, I have a few runners of my own that are sitting on a desk in our office at Google on our lab network. 3 Adreno 307s and 6 A630s that I maintain. By maintain, I mean I don't turn the power off. I haven't really had to do much with them. So the current testing matrix. Right now, every merge to Mesa gets tested on soft pipe, LLVM pipe, and the FreeDreno driver. So DEQP takes a good bit of time to run. So we take our test list and we shard it out. So soft pipe, we shard GLES2 4 ways. Just take every 4th entry in the test list, hand it to one job, take the other entries, hand it to another job, just split it out in a consistent manner so we get the same test runs every time. LLVM pipe, we do GLES2 and a fraction of GLES3. Unfortunately, LLVM pipe is rather slow at compiling the GLES3 CTS shaders. You can disable optimization, but I'm not sure how much value there is in running tests outside of the mode that end users will actually see. That seemed kind of silly to me, so I haven't bothered. Instead, I'm just doing a fractional run. I shard the test list 10 ways and just run one of the shards. So we can get that done in about 4 minutes. We're testing A307 on GLES2, and A630, we're testing GLES2 all the way up to GLES 3.1. As you can see, our slowest job currently on A307 is 10 minutes. I just landed or am about to land a compiler fix that will cut that test time down dramatically. It used to be under 5 minutes before some stuff went wrong. So getting compile times back down. I've got a couple of branches out that shorten our compiler time. Basically, the CTS spends its time software rasterizing reference images, because that's how a bunch of the tests work. Make a reference image and then run OpenGL and make sure that the two look the same or close enough. So speeding up our compiler is one of the main things we can do to get these test times down. So 2 branches out for that. One fixing a regression, another fixing some n-squared behavior in one of our optimization passes for certain kinds of input that the CTS really likes to generate. I'm working on Vulkan testing. I have a branch up that tries to do Vulkan testing on FreeDreno. As our FreeDreno Vulkan driver is currently immature, I'm not going to enable that because it ends up hanging the GPU a ton. We'll sort that out before turning it on. I would love to see more drivers tested. Sounds like Panfrost is going to get merged shortly. So that's using the Lava Lab at Collabra. And so pretty soon we'll be getting Panfrost tested on every Mesa merge as well. I was talking to one of the Lima developers. They're pretty interested in this too. If any other Mesa driver developers want to work on pre-merge testing, I would love to help you out with this. another next step, one of the reasons that the soft pipe and LLVM pipe aren't being enabled for GLES 3 the way which they can do, is our shared x86 runners assume that one GitLab CI job will take up about 4 CPUs, right? All of your make invocations we use -J4, DEQP is totally single-threaded, so I'm wasting 3 CPUs worth of time on our shared runners for all these jobs. So I need some little wrapper thing that will run DEQP in parallel and tell me the results at the end. For Lava, they're using this DEQP runner based on the Volt language, which I had never heard of before. I'm somewhat skeptical of pulling in a new language just for this, but one of my coworkers pointed out that he has a CTS runner written in C++ that does the same sort of thing, spawn a bunch of threads, run a bunch of DEQPs, collect the results at the end. So I've been looking into that one. We'll probably turn that on and get LLVM pipe and soft pipe tested across more GL versions soon. And then test other APIs, right? I want to do desktop GL. I want to test the Windows system layers, actually bring up a Wayland server, bring up an xserver, and see if the Windows system interactions actually work as we develop Mesa. That's it.
Okay, I'm Karen Ghavam. I think I met you briefly a couple of days ago. Wanted to talk a little bit about the Mesa regression testing we've been doing at LunarG for a couple of years now. I think many of you have probably seen it before, but I was also going to give an update of some changes that we're going to be making. So at share.lunarg.com, there is a system we run with each Mesa release regression test. It's trace-based testing on AMD and Intel Mesa drivers. And we have a pretty extensive library of traces that are coming from Steam games today. And we currently use the VK Trace, VK Replay technologies to do this. The real thing that I'm telling you about is that we're going to be deprecating that tool. It was created in a Fury, fast-paced way right before Vulkan 1.0 came out. We've learned an awful lot from our mistakes. We have done it right this time in the creation of Graphics Reconstruct. So I'll be telling you a little bit more about Graphics Reconstruct. I was going to just take a moment here to show you some of the features quickly. So we do both OpenGL and Vulkan testing on this. Right now I'm showing you the OpenGL test. There's a performance dashboard, shows the various hardware configurations that we're running. The performance dashboard lets you see with the performance tests over time how it's going. There's a limited window on the x-axis here. I can tell you a year ago, it was constantly up and to the right. So you Mesa developers were doing something right there. Once you go into a test request, and I have one already open here, you can look at, I'm just going to show you what you can do with images. So this is a test actually that had some failures, and you can bring up the image that's failing and of course get your standard XOR, difference here. You can look at the two images together, but visually you can't really tell what's wrong. So that's where this overlay comes in really helpful. Where you can toggle between the baseline and the overlay, and then you'll be able to see very well, what kind of things are going on. So that's just a really fast view of the tool. Going back to here. Okay, so so I talked about we had a big library from Steam games. We're moving over to Graphics Reconstruct on the back end of it. The solution is currently proprietary. It is our code internally. It's up on a server, on our AWS server. No logins required. Anybody can go out there and view the Mesa regression runs that we're doing with every release. But we are looking at options for open sourcing this right now. Okay. In terms of the tracing, so Graphics Reconstruct, it's new and improved. There's the URL for the GitHub, and we will be deprecating VK Trace, VK Replay, probably the end of this year, early next year. we will be moving that code into read-only. And we're already pushing back on fixes or issues that are coming in because it's just not really worth the time to do it. It's going to die. It's going to go away. The benefits of graphics reconstruct is we've really focused on having good Android support with this tool. It's given the same priority as the desktop solution. We rewrote all the code generation so that it could accommodate the evolving API. The way VK-Trace was designed, it was a maintenance nightmare with the Vulkan API evolving so quickly. So this code generation now, it will enable that to be much easier, lower maintenance. We increased the portability between x86 and x64. There's some cross-OS portability as long as you're using a compatible GPU driver combination. We've tested this on actually some NVIDIA proprietary Linux driver versus their Windows drivers. We could trace on Windows, replay on Linux, and vice versa. If it's italic and underlined, we haven't implemented it yet, but it's in plan. We will start doing this where we'll have some cross-vendor GPU support where you can trace on one GPU and play on another. We've integrated LZ4 compression for the trace data. Huge benefit because some of the files just got monstrously huge. And with this architecture, now you'll be able to easily put in other plugins that will be valuable, like generating C code or data mining utilities that you might want to do, what features is an application using, et cetera. So I think that's it.
Hi, everyone. I'm Nicolas Capens. I'm the tech lead of the SwiftShader project at Google. This is my first X.org developer conference. I'm very excited to present this. So for those of you who've never heard of SwiftShader before, it's a graphics driver for the CPU. I prefer not to refer to it as a software renderer because the CPU is hardware too, and we treat it as much as possible as a GPU. We encounter the very same issues. So if I take a little trip through memory lane, we started out many, many years ago with supporting DirectX 8 and 9. At the right side, you see Crysis running on SwiftShader. That was in 2008. Renders identical to what the GPU produces. Then we did OpenGLES 2 and 3. Google had a big interest in that for WebGL, and eventually also Android. And now we support Vulkan. And that is a fully conformant implementation of Vulkan, which I'll go into detail in. So taking a step back, Google is doubling down basically on wanting Vulkan everywhere. We have very major products that all centralize around Vulkan as the graphics API. So it was kind of natural when we first did OpenGLES for SwiftShader that we would do Vulkan next, but there wasn't like a key moment for demanding it. But then Android 10 now demands Vulkan as a minimum requirement for most devices. So there was suddenly a need to have sort of a reference implementation of this that could run tests and that would basically validate this architecture. So that's why we started what we called Project Pastel, which was a SwiftShader-based implementation of Vulkan 1.1, with just a minimum specification of it. But this was very foundational to our team for what's coming next. So here we see the architecture that we're dealing with today. On the left side of the dotted line, you see our old architecture for the OpenGLES implementation. We copied most of those layers over to duplicate folders, basically, and started implementing Vulkan. And we're transitioning to a Vulkan-only implementation. So if you look at our code base, you'll see Vulkan through the entire stack. We feel very confident in Vulkan being the future of graphics drivers. So we're removing every abstraction that you might find. And I could go into details about all of these layers, but probably the most exciting one to point out is Reactor. Reactor is a layer on top of LLVM and other JIT compilers. And it's inspired by this quote from Michael Abrash, that the fastest instruction is the one you never, ever execute. Now, you might think, oh, let's just jump over instructions that we don't need. but when you add jumps, you're adding more instructions. So the way we solved it with Reactor is to actually fully eliminate instructions from your functions by dynamically generating them at runtime. So here is an example of a full compiler written in Reactor. So if you copy-paste this, congratulations, you're now a compiler developer. This implements the brainfuck language, which is a very simple language, but still, this looks like an interpreter, but it's actually a full compiler. So for example, the P++ that you might see there in the middle of the screen, that's not actually incrementing P, that is calling the operator ++ on the object, then telling LVM, record this IR instruction for an increment in a very convenient way instead of like 5 or 6 lines of LVM code. So where do we stand today? We're fully Vulkan 1.1.3.3 conformant, ratified by Kronos. We're also Android 10 conformant. We support several CPU architectures, and we support the major desktop and mobile windowing systems. So where does it fit currently within other Google technologies? I'm sort of a person with one foot in Chrome and the other in Android, and both of them have a very big need for testing graphics and Vulkan in particular. So there's a lot of commonality between the two. I'd like to point out that Dawn is our project to unify Vulkan and Metal and DirectX 12 for the web. And it should also be a good target for Android portable graphics development. One of the things we did as part of Project Pastel is making sure we can test SwiftShader in very little time. We run a full DQP test run of GLES2, GLES3, and Vulkan in just 15 minutes on a very, very beefy workstation, but still, this made us super productive. And this is also important because we're testing Android a lot in our cloud instances. And the Cuttlefish device is our implementation of Android, a reference implementation of Android, basically, that can run much cheaper than having lots of physical phones in like a test battery. And today, LVM compilation is still a bottleneck, but we're looking for a lightweight jet replacement that is going to make it even faster. So I'm going to show you a little demo of it all. And hopefully that works. Yeah. So if you haven't noticed, this is a MacBook, and this is a fully conformant Vulkan 1.1 running on a MacBook, the first. I also have Quake 3, if anyone's interested in doing a deathmatch. That's it. Thank you very much.
So my name is Jason Gerecke, and I am one of the input developers that works at Wacom supporting graphics tablet. And I've been working on, I've been having this idea about reducing some latency for drawing for the past year since last XDC, when I talked with a couple of graphics developers, some of the Mesa devs. And I wanted to throw out an idea for how we might be able to reduce latency under Wayland. A quick disclaimer, I don't actually know a whole lot about how the graphics subsystems work, since I'm one of the input guys. Like, a lot of what I say is just sort of my best understanding of what's possible. And it's entirely possible that what I'm suggesting isn't doable, or that there may be better solutions out there. And so I definitely welcome feedback if you guys have anything that you might suggest for how to make this better. So the issue that I'm trying to address is input lag. As you can see on this image here, I'm just drawing a line in GIMP on a somewhat realistic scene, and we can see that like the first pointer on the left is where my pen is. The next circle shows where X is rendering the cursor, and then way over to the right, 75 milliseconds behind me, is where GIMP is actually last painted. A 75 millisecond delay is noticeable. It could be worse. There's network delay that can be a real problem and is becoming more and more of a problem as studios start to move towards remote and satellite work. And so trying to figure out how to reduce this as much as possible, ideally 0, but I mean, we can certainly try to catch up with the cursor that's painted. There's a couple of ways that lag is attempted to be reduced right now. You can do things like get a higher refresh rate display, and fewer frames behind means fewer milliseconds. You can disable VSync. That way you're not necessarily waiting for those for that 16 millisecond penalty every time. Tearing isn't really a big issue when you're just drawing. Over the network, large studios actually have dedicated networks that they run between LA and Vancouver just to bypass general internet latencies. You still obviously have speed of light to deal with, but that's a separate issue. In software, there's things like input prediction that we can do. Compositor acceleration is done under Chrome OS and a couple of other systems. And again, over networks, you have the concept of a local cursor, which is displayed rather than trying to show where the remote system thinks your cursor is, which is a truly horrifying experience. So the basic idea is, let's try to wrap up some of these basic software optimizations that already exist into one simple protocol. That way, each application doesn't need to know all the various optimizations that they could do to reduce latency. So you'd basically have your application signaling its intent to use a surface for inking, and then the compositor is going to optimize that surface to provide the best inking experience. So that could mean disabling VSync if possible, rendering directly to a frame buffer or some kind of overlay plane. And this is just going to reduce those delays, ideally getting it to possibly not getting all the way up to the cursor, but reducing that 75 millisecond delay significantly. And like I said, some of these low latency APIs are already available on other systems, and it'd be nice to have that in Wayland. Rapid is kind of an extension of this basic idea, trying to get the latency as close to 0 as possible. And the idea here is that you could basically, again, have your application signal intent to use a surface for inking, and then the compositor, in addition to applying those basic optimizations, would do its own painting on behalf of the application. This would just be temporary ink, an approximation of what is going to be happening over the next few dozen milliseconds. The compositor already has access to the input events, the surface transforms, it knows where to paint. All that really needs to happen is the application needs to tell it approximately how big the cursor needs, or how big the brush needs to be, approximately what color it needs to be. And by doing this, you can basically get all the way up to where X is right now, just one frame behind the actual pen position. Over the network, if you have a compositor that is working remotely, you can hide that entire network latency again as well, because the local compositor is receiving these input events and immediately rendering to them to the display, rather than waiting for an image to come back from a server a few thousand miles away. And this is similar to what some mobile devices do, where they have very slow displays that need to fast path their input events into inking. So like I said, perfect ink fidelity is not really required for this to work. We're just providing some feedback so that the user can get an idea of what's happening. The real ink is going to be there in a few dozen milliseconds. And so like just doing a sequence of line twos, totally fine. Approximating the color, brush is totally fine. You don't need the exact brush outline. There's a couple of ways that this could be implemented. You could have the application, or have the compositor rendering ink into a buffer and then erasing that ink as it gets damage updates from the client. You could just have a static pointer trail, 100 milliseconds long. Any of this would be a really easy way to hide all of that latency that's currently there. So again, hunt me down in person. I'm pretty sure that there's parts of this that could be improved, so do let me know. Thanks.
there is still an xserver. It still gets changes. It gets bug fixes every once in a while. There are like some minor features that need to get added. They need to get released on some kind of schedule. Absolutely none of you have stepped up to do anything about that since May of last year when I said I'm not doing it anymore. So, what we're doing, since we're all in this lovely, like, CI is an awesome thing future, we're just going to keep adding tests to CI right now. Everything that goes into xserver get master has to pass the XTS, which is not saying much, but it is something. I'm going to start enabling more tests as we go. Right now, it only covers a subset of the rendering test. We're going to start adding on, like, yeah, you didn't mangle the window tree. We're going to start adding render checks, starting adding a bunch more stuff as we go. That all needs to keep happening. And then once or twice a year, just going to pull the lever, and it will be a release. Probably May and November, just because that happens to be convenient for the releases I've got. If anyone wants to suggest something better than that, please do so. The one thing that we do want to be careful about, the last time we changed the xserver's version number, we really screwed it up because we epicked, and we went back from like 7 billion something, 7 million, 70 million, to 1 million something, and a bunch of software got really confused. So we're not going to do that. This is a scheme that lets me change the versioning system to be year numbered, which is really cool, and everyone's doing it these days. So this lets me do it without having to epic anything. 1.20.5 looks like that right now. 1.20.19 will be 1.20.19. And then the last bit we're actually going to use for the minor releases. Cool? Cool. Stable releases, same process. Everything that goes onto a stable branch, pull the merge in. Every 2 weeks or so, if there's been any changes to the stable branch, pull the lever, new release pops out. If you want something else, congratulations on your new job as the release manager. That's all I got.
How to pick easy project names. We all know the two hardest problems in computer science are cache invalidation, project naming, and off-by-one errors. It's a quote by Jeff Atwood, I think, or somewhere you can Google it up. For the second problem, at least, languages come to the rescue. According to the first website that I clicked on, there are about approximately 6,500 languages in the world. Presumably, at least one of them has a word that sounds cool enough that you can use it as a project name. The internet's come to the rescue here. Google Translate. It's a bit annoying because you have to do it one language after another. But there's a website like indifferentlanguages.com, which I recommend for that. For example, this is the various versions of the word fail for your next project name. So, for example, if you like Czech, you can name the project Cellhat server or whatever you're going to implement now, or Faller in Galician, or Fehlgeschlagen in German if you want that. That one has about 100 languages or something. Some of them sound cool. All you have to basically do is find something that even English speakers can pronounce. I do recommend, do double check, find a native speaker, make sure the word really, really works. You don't want to really copy the Mitsubishi Pajero mistake. If you don't know what that is, check the Wikipedia page. That's all there is.